So our next step in geology is to start looking at geologic time. What has all of this geology stuff actually told us about the history of the Earth and so on? So one thing that we have learned is that the Earth is really old. Based off of everything we can tell, the Earth is about 4.5 billion years old. That's billion with a B. And to kind of give you a sense of scale, we're going to compare the entire history of the Earth to a single year. So the formation of the Earth occurs on January 1st, and then right now, at present, is midnight on December 31st. So with this time scale, the very oldest rocks that we still find occur towards the end of February, around February 26th. We see the first signs of bacterial life around March 23rd. Dinosaurs, which at least for me is something that I think of as so far in the past, super ancient, actually occurred between December 14th and then they went extinct around December 26th. Homo sapiens, so our species first appear, we find the first evidence of Homo sapien on December 31st at 11:50 p.m. And then all of human history is within the last minute, from starting at 11:59 on December 31st. So, in other words, the Earth is really, really old. So how is it that we actually figured out all of this stuff? Hey, well, we have an underlying assumption known as uniformitarianism. It's a really long word, but it actually has a relatively simple idea. Specifically, the idea is that all natural laws have been the same throughout all of geologic history. In other words, the same sorts of things that create features today are the same processes that created features long ago in the past. So as we understand how things are made now, we can then know how they were made in the past, and that all of these things are consistent throughout time. Okay, so in this way, we can figure out what went on in history. Well, as we look at the rock record, there's actually a couple of ways we have of trying to figure out how things occurred. Okay, the two methods we have are relative dating. Okay, what this means is we're actually looking at the relative order. How is it that things happened compared one to another? The other is radiometric dating, or also called absolute dating. And in this case, we're actually trying to figure out the exact age. How long ago did this happen, and for how long did it happen? Okay, so to help kind of understand the difference between relative dating and radiometric or absolute dating, we can actually look at how it is we treat time ourselves. For example, if I tell a friend, hey, let's go to the movies after class, this is relative. I know that we are going to go to the movies after class. Now, I did not say when class was or exactly when the movie was, just that after class, we are going to the movies. Absolute dating, we actually give a time. So, for example, I could say, hey, let's go to the movies at 7 o'clock. Then we have an exact time related to it. Okay, so relative dating is the order or sequence of events. Absolute dating, we know the exact time of when it happened. With relative dating, there are several principles we use. The first one we're going to look at is original horizontality. This states that sedimentary rock are always originally horizontal. So as you think about a flow of water from a river into a lake or into the sea, the water flows in, slows down, and then sediment settles out of the water. But because of the way gravity works, those layers are going to start out flat at first. This is the entire idea of original horizontality. Sedimentary rock layers should start out horizontal. If there's any sort of tilting, like what we see in this image, or bending or breaking, all of that had to happen later. All sedimentary rocks begin horizontal first. All right, here's our first question for today. In a stack of cards, which card was laid down first? So imagine you're playing some card game with a discard pile. Okay, which one is going to be laid down first? I should also state, assume you're playing with adults who keep the pile relatively neatly. You're not playing with 2 or 5-year-olds who just throw cards anywhere. We're keeping a somewhat ordered stack. A, the card on bottom of the stack. B, the card on the top of the stack. Or C, there's no way to determine in which order the cards were laid. Go ahead and think about it, and we'll discuss it in just a little bit. All right, so what do you think? So, as you play card games, you lay one card, and then you play another card on top of that, and another card on top of that, which means that the card that is on the bottom has to be the one that was laid down first. Okay? And so the farther down the stack you go, the longer ago the cards were laid. This is essentially the idea of superposition. So when we are looking at undeformed sedimentary rock layers, the younger layers are on top of the older layers. So again, if you think about how it is that stuff flows into a stream, you get sediment carried in by the stream into a lake, the sediment then settles down, and then the next year's stuff flows in and settles down. So we get layer on top of layer. So the bottom is the oldest and the top is the youngest. So another principle that we can use is cross-cutting. The idea of a cross-cut is that whatever is cutting through has to be younger than what is being cut. The thing had to be there for it to get broken apart. So in this case, on the left, we have this black rock, which is pushing up through a bunch of sandstone. The sandstone had to be present before this black rock pushed up through and broke it. On this right one, we have light granite cutting through darker granite. The dark granite needed to be there for the lighter granite to be able to fill in the gaps. Another principle we use is the principle of inclusions. Anytime we have one kind of rock surrounded by another type of rock, whatever is included, the thing that is inside, must be older. It had to be there already before the new stuff flowed around it. Okay, so again, going back to a lake. One year, maybe you get a huge boulder that plops down in the middle of the lake, and then over time, you start to get more and more sedimentary rock building up around the boulder in the middle. So the boulder had to be there already to then get surrounded by the other material. So in this case, we're looking at 2 types of granite. We've got dark granite that is completely surrounded by the light-colored granite. This dark stuff had to be there before the light stuff could form around it. Now this is also corroborated, it agrees with what we see in a crosscut over here on this side. We see that the lighter granite is cross-cutting through the darker granite, again showing that the dark granite had to be there before the light stuff came through. Now I will admit that sometimes being able to tell whether it's a crosscut or an inclusion can get difficult. Okay? But if you can tell, this is one way to figure out what happened in what order. Another principle we use is lateral continuity. In lateral continuity, we can actually look at large areas and look at different rock outcroppings and look for similar characteristics. For example, in this case, we are looking at part of the Grand Canyon. And as we look at these different rock outcrops, you can see how it is we get these different layers. Well, that tells us that the sequential order in one rock region, in one outcrop, is going to be the same in another. So we can infer from one what's going on in the other. Our last principle is the principle of faunal succession. The idea of faunal succession is how it is that fossils change as we go through different layers of rock. There's the steady progression that we see of the change of fossils. So, for example, we might look at a low layer, and in this, we might find moths and trilobites and clams. In a more recent layer, we no longer find trilobites. We might still pick up clams, but we'll now find birds and dinosaurs, which we didn't find before. Okay, so looking at the sequence, how it is that the fossils and the rocks are changing, can also help us figure out the order of what's going on. Now, one problem we have with relative dating are unconformities. An unconformity is a gap in the rock record, a region where, due to weathering and erosion, the rock record has been destroyed and removed. Okay, so these are unconformities, places where we no longer have all of the complete rock record. So, for example, in this bottom right, we see this kind of wavy stuff, and then we get new sedimentary rock on top of it. Because of all of that, we are missing some information. That, this transition through here, this is the unconformity. All right, let's see if we can put all of everything we learned into practice. See if you can figure out what order all of these things happened in. Go ahead and give it a look for a little bit, and then we'll start talking about it. All right, so what do you think happened very first? Based off of what we see, it looks like this layer here, the orange stuff, which is E, had to happen first. And then after E, then we get G, and then we get green, which is L, kind of hard to see. And then last, we get this kind of brown one, which is C. So we have E deposited, G, L, and then C. Now, after C was deposited, notice how we get this break. So that suggests that H happened next, and then also probably some kind of tilting, because remember, original horizontality. These should be horizontal first. Okay, so we have fault H, which probably also led to some tilting. Now, after fault H occurred, then we see some unconformity. You can tell, based off of how these rocks are laid down, that they should continue, but they don't. So this region has been weathered and eroded, so we now have an unconformity. Then after this unconformity, we next have M, then D, and it's hard to see, but this kind of yellow brick is J. So we have M, D, and J were all deposited. Then after those were placed, then it appears that A pushed in through, cutting through everything. Okay, so it then broke through all of these lower layers, but then also M, D, and even broke through some of J. So it appears that A likely intruded at this point. Now, after A intrudes, then we get another unconformity, weathering and erosion. It looks like A and possibly J should continue, and they don't. So after A intruded and the unconformity, then we see N, K, and B were all deposited, but again, they should be flat to start with, so then something must have occurred. So we get some sort of tilting, and then also, it looks like all of these should continue and don't, so we get some sort of weathering and erosion leading to an unconformity. And now we see the surface layer, which is F. So F is currently being deposited, although we also see some erosion of the current surface. Okay, I hope all of that made sense, putting in all of the pieces that we've talked about, seeing how it is these layers go together. Now, I do want to warn you that something like this will be on the test, where I'm going to provide a picture and you'll kind of have to figure out the sequence of events. So be warned, get it now. Well, to help you with that, we've got a couple of questions. So here is question number 2. We have 3 dikes, meaning igneous intrusions, cutting into a rock body. Which dike is the oldest and which is the youngest? So go ahead and look at the image and figure out what is the sequence that these happened in. All right, so looking at this, we see A has come through, but it is not broken, but it is cutting through B. So this suggests that A is younger than B. Now, when we continue to look at B, we see that B is cutting through C, which means C had to already be there for B to cut through it. So C has to be older than B. So this means that C has to be the oldest, and then B, and then A is the very youngest. So the correct answer for this is B. All right, here's another piece. Go ahead and look at these rock formation and decide what's going on. Okay, so the embedded rocks, we're specifically talking about these granite pieces within these sedimentary layers. Okay, so the embedded inclusions in the sedimentary layers are A, metamorphic, B, older than the sedimentary layers, C, younger than the sedimentary layers, or D, the same age. Go ahead and think about these and we'll discuss it in just a bit. All right, so we have these granite pieces which are surrounded by sedimentary rock. That means these granite bits had to already be there for the sedimentary rock to flow in and fill in the gaps. So the inclusions must be older than the sedimentary rock layers. So the correct answer is B. I hope that kind of helps you see how we do this relative dating, figuring out the age and sequence of events based off of the principles we've talked about.